Hello and welcome to Wilcoxon and the MannWhitneyU. So today we're going to look at the WRM statistical tests. We're going to explain why you and when you would use them, and we're going to go through some worked examples. So the Wilcoxon and MannWhitneyU tests are both non-parametric. And remember, we said that parametric tend to be a bit more powerful and scientists generally prefer those. We use non-parametric tests when we've done something with the data, and what you're going to see with Wilcoxon and MannWhitneyU is that we actually rank the data. So we're not taking the raw data from the table in a sort of interval form, we turn it into some ordinal data and then we use that in our test. So let's start with the Wilcoxon test for related designs. Related designs is just another word for repeated measures really, and what it means is the data are related. When do you use it? Well, you use the Wilcoxon if the hypothesis states a difference between two sets of data. You use it when you're looking at paired or related data, i.e. scores from the same person, or any data coming from repeated measures or matched pairs design. It operates at the ordinal level because we're going to rank the information, and there are not equal intervals between the ratings, so it might be IQ scores that could be ranked in order. Looking at information produced before and after cognitive interview training might be an example. So you have a score, the number of items that they recall or can elicit from their witness before the cognitive interview training, compare it to the number of items after. Difference in number of words recalled at the beginning and end of a list. Difference between depression scores before and after CBT. These are the types of experiments that we could use this Wilcoxon for. Right, so here's the procedure. We start off by stating the hypothesis. It has to be one or two tailed. For example, people's scores on a depression inventory will be significantly lower after CBT than before. So a precise testable statement predicting the outcome of the study. Then we place the raw data in the table. So we have our participants N, we have their original score, and then their second score. So we're saying their score should be lower in the second column than it is in the first. Kinda looks good so far, couple of blips, but we'll never know until we carry out the statistical test. So what we have to do is we have to calculate the difference between these two values. So in this case 10 minus 7 equals 3, 15 minus 9 equals 6, and so forth. When you get two values that are the same, you leave it blank. Based on the difference then, we then rank them. Now when you rank, you ignore the sign. So in this case 2 is the lowest number in our difference set, so that gets 1, the lowest ranking. Then 3 is the next lowest number, so that gets 2. 4 is the next lowest number, so that gets 3. 5 is 4, and then we've got 2 6s. Now here's where students always find this a little tricky. What you have to do if you have two values the same is you can't just give them the corresponding two ranks. That would be in this case 5 and 6. What you have to do is you have to add up the number of occurrences, those two ranks together, i.e. 5 and 6, and then divide them by 2, because we've got 2. So in this case we come out with two 5.5s, 5.5 for this 6 and 5.5 for this 6. Alright, so they sit at the rank 5.5 and 5.5. Now because you use 5 and 6, you have to jump now to 7, and the next lowest number is 10, so that becomes number 7. It's a bit tricky, but if you practice it enough, it will just come to you. So the idea is if you have two numbers the same, you add their ranks together and divide them by 2. If you had 3 numbers the same, you would add those 3 ranks together, so in this case it would be 5, 6, 7, divide by 3, and each of the ranks would, each of the numbers would get the same rank. Right. Now this bit's quite easy. We then sum the ranks of the less frequent signs, so in this case we only have 2 minuses and the rest are plus or neutral. So we sum the ranks of the 2 minuses, in this case 1 plus 4, therefore t, your t value, equals 5. Now we want to check the directional results and then compare it to our critical values. So here's our critical value table. We're working at a significance level of 0.05. That will always be constant unless they tell you otherwise. Find the critical value. So in this case, how many participants did we have? Well, we had 8 sets of data, but we had to remove a set because there was no difference. So we wound up with 7 in total. If we look at the column 7, 0.05 is our value, therefore our critical value is 3. Now, remember we have this greater than or equal to or less than or equal to. In this case, Wilcoxon does not have an R in the title, and therefore the calculated value, i.e. t, should be less than or equal to c, the critical value. So if t is less than or equal to c, then the results are significant. In this case, t is 5, and it is not less than or equal to 3. Therefore, we accept the null, reject the alternative, and suggest that CBT does not significantly reduce depression scores as our hypothesis indicated. This is a little extension, you can zoom past this, but it's worth just noting this. I mentioned this before, that actually as the numbers go up, i.e. the participants or sets of data go up, the threshold is decreased. And you can see this quite well in our table. At 7 participants, we need a value of 3 or less. And we didn't achieve that, our t-value was 5. But if we'd just had one more set of data that was not neutral, this would have resulted in a positive finding. We would have shown a significant difference. So this just shows that as the participants go up, the threshold and likelihood of achieving a significant result also increases. So that's just a quick recap to sample size. Right, the Wilcoxon is very easy to calculate. The Mann-Whitney-U is a little more complicated, and we'll see this now. The Mann-Whitney-U is for unrelated designs, that's independent groups usually. When do you use it? You use it when the hypothesis states a difference again, same as Wilcoxon. When the 2 sets of data are from separate groups, i.e. they are unrelated, and the data are ordinal because they do not have equal intervals between them and can be ranked. So an example would be the effects of SSRIs at reducing OCD symptoms. 2 groups of OCD patients, one received the SSRIs and the other receive a placebo. And another example might be females will rate males with higher salaries as more attractive than the same males with lower salaries. This is an independent groups unrelated data design, and therefore we can use Mann-Whitney-U. Right, this is a bit more complicated then, but we're doing something very similar to the process involved in the Wilcoxon. We state our hypothesis, decide if it's going to be directional or non-directional. Here we're going to say females will score males with higher salaries more attractive than the same males with lower salaries. I don't really like this hypothesis. Males with higher salaries will receive will score higher on the attractiveness scale by women or something like that. But it works, it works. We place the raw data in a table. Now we've got separate groups. So we call this column A and column B. In this case, these are the high salary maybe, or the low salary, depending. You then rank each set of data, same as Wilcoxon, but remember, each set of data must be ranked independently. So in other words, we rank the entire data set. We look for the lowest one overall, which in this case is 1, and we rank that 1. We then look at the next lowest one overall, and that's 2, and we rank that 2. We look at the third lowest overall, and here we have a tie. So we do the old 3 and 3, they take up spot 3 and 4, we add up 3 and 4 divided by 2, and so forth. So you rank them. Once you've ranked them, you add up the number of participants in each column. They do not have to be the same. And then you calculate the RA and RB values. All these are is add up your ranks for column A, add up your ranks for column B. You take the smaller of RA and RB, and that's the figure that you put in your statistic. This is your calculation then. To calculate U, you take RB in this case because RB is smaller. You take RB, you minus from it NB multiplied by NB plus 1 divided by 2. In other words, 80.5 minus 11 times 11 plus 1, which is 12, divided by 2 equals minus 14.5. Right, now we've got to see if it's significant. So here's our critical table. It's a bit different from some of the others you've looked at. We've got NA11, NB11, so we find the 11 value. Critical value then is 34. Our U value is 14.5, and we have to state, because there's no R in the Mann-Whitney, is U less than or equal to C? In this case, U is 14.5. This is less than or equal to 34. Therefore, we reject the null hypothesis, accept the alternative, and suggest that females will score males with higher salaries as more attractive than the same males with lower salaries. Therefore, we have a research finding. Right? This table is only for the p-value of 0.05. You get a separate table for a two-tailed hypothesis and other p-values. So those are the Wilcoxon and Mann-Whitney-U tests. That's a bit of a whiz through that, and you might need to go back and revisit some of it. Just to recap then, it's a test for difference, Wilcoxon, related data, i.e. repeat measures, difference is ranked, calculate T, T must be less than or equal to. Mann-Whitney-U, very similar, test for difference, except this time it's for independent groups, unrelated data. Scores from each group are ranked in an overall scale. U calculated, U must be less than or equal to critical. Okay, that's the presentation with the knowledge. What I've got now is a couple of practice questions which you can work through to see if you really understand it. It might take a few goes before you get it, and then next lesson we're going to take your data that you produced and chuck it into this test.